So our first texture problem that we come to is magnification. So remember, magnification is over here on this side. This is when we zoom up our texture. So each pixel on the screen comes to a small place where there's basically too many pixels packed together in our texture. Our texture has too low of a resolution. So this is the easy case. We've already, in fact, talked about the solution to this in this class. So if we just take nearest neighbor sampling, we're going to get pictures like this when we zoom in. But we've talked about bilinear interpolation. So let's just quickly look at how that applies here. So we have our screen space zoomed in. Our pixels map to these sub-texture locations, right? This is our samples in our texture, and these pixels map to the in-between places. So what are we going to do if we need a color that's in between, right? This means the texture has a color stored here, a color stored here, a color stored here. How are we going to look that up? Well, in fact, you've all studied how to do this already, right? This is basically says we know these colors. We wish we had this color. So what are we going to do? Bilinear interpolation. Here's our 4 samples. We're going to set up a grid like this and say we know what they are and calculate the color at the point red. So we're going to do a linear interpolation, find these points with the 2 helper linear interpolations, interpolate into this final step, and then we get this bilinear interpolated picture. So dealing with magnification, we don't get a perfect answer. It's of course blurry, but we know what to do. We know how to look up in our texture if our texture is too low resolution. This is the best you're going to get if your texture is too low resolution, and we know how to take those steps. And indeed, you can set up your graphics to do that for you. So you can, when you look up a texture in WebGL, you can tell it to do this operation. Minification is the thing that's a little harder, and we're going to take a little bit longer to talk about because it's a concept that's a little bit more challenging for people to get their mind around. So this is at the other end. What does this mean? This means I have too high of a resolution of a texture. Well, how can that be a problem? Go ahead, just give me a texture, 10K by 10K, a huge texture, 100 megapixel. Like, it won't be any problem. Every time I look up a pixel, I'll be able to map it to something. It turns out this is in fact a problem because there's too many pixels inside my texture that I need to somehow munge together. So let's look at what's going on with this same picture. Here's our screen pixels, and now my pixels are widely spaced. And suppose there was an important color on this texture point, and we're going to miss that important color because we're going to skip over. So here's another picture showing the same thing. So here's our texture space. So it's flipped around from what we had earlier in our slides. Here's my pixel. This pixel maps to a large texture space. You can get these kinds of problems in the back. So this is a form of aliasing, and you get weird randomness in what's going on in the back because there's essentially too many pixels that you randomly pick from. So I'm going to try to give a more ordered example because I think this is easier to understand. We have neighboring pixels, and they've skipped over in the texture. This is my texture now. And so this pixel on my screen maps to here, and this pixel on my screen maps to here, and we've skipped green in this. So now let's look at a real example. So here's my teapot with a yellow texture with thin red lines. What happens when you skip over? Oh, I'm missing parts of the red line. They didn't come out. This is not what you want to happen. So this effect is also aliasing. This is the same as we saw with the checkerboard in the back, but I think this is easier to understand. Why does it happen? I skipped over, and so I missed the red line. So I really wish I got a picture that was more like this, right? So it's not perfect red because it's the merger of red and yellow. What really should go in this pixel when I look up the texture should be the average of the neighborhood in the texture. And the average color is going to be this part red, part yellow. This is going to get filled in. So said another way, when my pixel maps into my texture, it's going to cover some range. And it might be just within a single pixel, and it might be covering a large region of pixels. And I should somehow average all those things together and stick the average back in this color. This is what I wish I was going to do. So now we come to the problem for minification. We'll talk about the solution in our next little subsection. But our problem is I have too many pixels here. I wish I got the average and put it there. How are we going to make this fast? Right? It's all nice to say, well, you just average all these pixels together. But if this square was 100 by 200, I would have 20,000 pixels that I have to go look up and average together. And I don't want to do that in real time for every pixel on my screen. So I'm going to need some methodology to make this faster. And that's what we're going to get to next. But let me see, is there any questions about this problem and what causes this problem? This notion of minification and the fact that we skip over pixels and we need to somehow include them in our averages when we get the colors on the screen. Okay, you guys are welcome to ask questions. I think audio questions, save them for when I say the questions at the end. Chat questions, type them anytime, and then I'll be able to see them when I get to the end if you're desirous to do that. So mip mapping is our answer. So this is a funny word. It's a graphics word. It's something that you can turn on in your graphics card. It comes from this 1983 paper by Lance Williams. This thing is a mip map. We're going to talk about this in more detail. So what is it? If we have a texture, in this case a 64 by 64 texture, we store a sequence of lower resolution. Because remember, our problem was our texture was too high a resolution. But we can't just reduce the resolution or some other things will get blurry. But we're going to calculate these lower resolutions. So 32 by 32, 16 by 16, 8 by 8, 4 by 4, all the way down to 1 by 1. We're going to store all these different levels. And one of the key insights in this original research paper was, oh, that's a bunch of extra storage. But really, when you pack it, it's only 33% more storage, right? This was my original texture in RGB, and it all packs together. So it's not too much more storage to store this format. Why mipmap? Mip is from Latin multum in parvo. So I mean, it's many things in a small place. So, but people just call it mip mapping and don't worry about what the naming came from. Here's another picture showing the same thing. Here's my original texture image. And what you're really storing is these lower resolution. I like it drawn smaller and smaller because it helps think about how much storage is getting used. But another way to say would be, think about it as the same texture, but with less and less information in it. So this is also another useful way to think about the same thing, I think. So as my pyramid levels go down, I'm storing less resolution in this texture. So why do I want this thing? Okay, at texture level 0, meaning the full resolution, my stuff up close is going to look okay, but I'm going to get aliasing in the back here. This was the skipped over red lines and the weird jaggy stuff on the black and white. You're going to get aliasing, and this will be visible if you have animation. So even you can't really tell in this picture that there's aliasing happening. As soon as things start to move, you're going to get weird shimmering artifacts. And so you'll be able to see that aliasing on there. We go to level 2, we're kind of okay on both. By the time we get up to level 4, we significantly blurred the foreground. So the back is going to be right, but the foreground is going to be blurred. Right? If we scroll back, remember we had information here on the foreground. And at our lower level, we've thrown away that resolution in our texture. So we can't just pick one level. We're going to have to be smart and use all the levels somehow. So how are we going to pick the right level? So when we're rendering, so this is done, the picking of levels is done in the graphic system. We don't have to do it. So here's our triangle. We only specified information on the vertices. Internally, it rasterized. It knows which pixels it's about to call the fragment shader on. So it knows the UV values for this pixel and the UV values for this pixel. And so where do they map in texture space? So this pixel is going to go to here, one of these here, and this pixel is going to go to here. And the fragment shader is going to be called for these two values. So internally, it knows how big this is between the neighboring pixels. So it can do a calculation that says, if I consider all of my neighboring pixels, how far away were they? Calculate some derivatives or differences from the neighbors, and then calculate some size, where if the size is 1, we want to use the top level of the texture map. And if the size starts to get bigger, then we're going to go down in levels of texture map in order to make it to be 1. So here's a visualization of what those different levels are. So these things up close are going to be at one level of the mip map, and these things in the back are going to be at a different level of the mip map. You thought bilinear filtering was giving you a headache. There's such a thing as trilinear filtering. So what does that mean? I'm on mipmap level D, and I do some bilinear interpolation to get a color. And then on my next level of the mipmap, remember my resolution is half on each dimension. So now I'm going to do a lookup on this level. And then based on this color calculated here and the color calculated here, we interpolate between those and we get a final position for our trilinear mapping. So I'm not going to make you work out the math on that, but your graphics card does this internally to do the lookup on two different levels and interpolate in between. This picture may help think about it. So if I have a pixel and it mapped to this crazy shape over here in my texture, well, this shape has, I don't know, roughly 9 pixels in it. So, and this is calculated using the way that I showed you. Given these 9 pixels, well, I don't have a 9:1 level of my mipmap, right? I have a 4:1 and a 16:1, so it must be between these two levels someplace. So we're going to go calculate the color here, which is a lookup with a bilinear interpolation. Calculate the color here, look up within the bilinear interpolation, and then do a final linear interpolation to get my final color out. So a bunch of texture access, a bunch of memory access is happening every time we do a texture lookup, according to this, to try to get things to look better. So what are we going to get from trying to do this? So here's our ground truth answer. This is what we wish that we were getting. If we do mipmapping, what are we going to get? Well, notice in the back, we got a little more blurry than we wanted to get. So there's too much blur happening back here. But we didn't have crazy things happening. It didn't get all jaggy and weird. It just got a little bit overly smoothed out. Let me show you again. This is what we wish we were getting. Here's the over smoothing that's happening in the back. So we're going to come back and talk about why this over smoothing was happening. But mipmapping allows us to take care of the weird things happening, and this will animate smoothly. So if these were just random, in this case, blue and black pixels in the back that were flickering on every frame, that would drive you crazy. It's better to have it smoothed out like this. Okay, here's some examples. So here's my texture image mapped onto something going in the distance. Here's point sampling. We don't turn on any of these fancy features. So there's no bilinear interpolation happening here in the front, right? We didn't smooth out our colors. And in the back, it's basically random black and white pixels. Here we've turned on bilinear interpolation, but not mipmap filtering. So I've smoothed out in the front, but I haven't done anything about the random pixels in the back. Here we are not doing the bilinear interpolation, right? Because this is where the magnification, bilinear interpolation happens with the magnification. We have not done that, but we did do mipmap filtering, which is smoothing out what's going on in the back. And then here we've turned on both. Both are turned on in order to get this kind of effect.